In this recording, we look at integrating rational functions that are a degree m polynomial divided by a degree n polynomial where m is greater than or equal to n. So for instance, a cubic divided by another cubic or a cubic function divided by a quadratic function would be examples of this. There's a four-step process we need to follow here. First, we use long division to rewrite the rational function as a polynomial plus a proper rational function. That is a polynomial plus a rational function where the degree of the numerator is less than the degree of the denominator. Then, the polynomial part of that will be straightforward to integrate, while for the proper rational function we factorise its denominator, which will still be the same as the denominator above, into a product of linear and or irreducible quadratic factors. And if it does factorise into more than one such factor, we then rewrite it using partial fractions, and from there it will then be possible to integrate the resulting expression. So let's look at integrating the following rational function, and here we will assume that you know how to use long division of polynomials and how to convert an expression into partial fractions. So if you don't know about those things, you might want to refer back to our MathsCasts on those topics. So here we have an integral where we have a cubic divided by a quadratic. That is a degree 3 polynomial divided by a degree 2 polynomial. So the first step will be to use long division. 2x cubed plus 3x squared minus 61x plus 24, where we'll be dividing that by 2x squared minus 13x plus 6. And when we do this, you can verify we actually end up with x plus 8 and a remainder of 37x minus 24, meaning that it is plus 37x minus 24 divided by 2x squared minus 13x plus 6. So that is the first step. It is now rewritten as just an ordinary polynomial, which in this case in fact is just a linear function of degree 1, and then plus a proper rational function, where you'll notice that for this expression here, the degree of the numerator is 1 and the degree of the denominator is 2. So now we look at this part before doing any integration, and we factorise the denominator of that if possible. And this denominator will in fact simplify or factorise to become 2x minus 1 times x minus 6, and therefore, because it is now a product of linear factors, we can rewrite this using partial fractions. Applying partial fractions to that, it comes out to be 1 divided by 2x minus 1 plus 18 divided by x minus 6. So that means that the original expression we started with is now able to be rewritten as x plus 8 plus the partial fractions form of this part. So plus 1 divided by 2x minus 1 plus 18 divided by x minus 6. And we're wanting to find the integral of this expression with respect to x. By the linearity rule for integration, we can break that up as follows: integral of x plus 8 with respect to x plus the integral of 1 divided by 2x minus 1 with respect to x plus the integral of 18 divided by x minus 6 with respect to x. And each of these individual integrals is now straightforward to evaluate. X plus 8, that will integrate to give x squared divided by 2 plus 8x. 1 divided by 2x minus 1, integrating that by substitution with u equals 2x minus 1, we'll find that that becomes a half times the natural log of the absolute value of 2x minus 1. And similarly, 18 divided by x minus 6, integrating that, it will become 18 times the natural log of the absolute value of x minus 6. And finally, all of this is plus a constant c. So that is the integral of the original expression that we started with. So the main process, because the degree of the numerator was greater than or equal to the degree of the denominator, in this case it was greater than it, we used long division initially. We then, using the proper rational function that resulted, we split that up into partial fractions, and then that allowed us to then integrate our expression term by term to obtain our answer.